In this research project, I want to talk about hypointensity lesions or MS lesion segmentation using attention mechanism in MRI images. MS is an autoimmune disease that causes lesions in the brain's white matter tissue, and we use MRI to visualize and diagnose this kind of disease. And the problem and the challenge here is that the lesion segmentation over data set, which is very small, makes learning more difficult because model overfit. So to address this problem, we came up with 3 approaches or novelties. First, we use 2 modalities of data, try to have 2 passes of information for each of those modalities. Second, we create a pipeline that uses attention mechanism to pass information globally on the patches of data. And we want that pipeline on both of 2 modalities. And this attention module also has these features that has a spatial and channel-wise attention. We know that CNN-based algorithms for medical image segmentation are divided into image-based and patch-based methods. So the previous works, when you have such limited data, many of them try to approach this problem using patch-based method. So you can increase the number of training samples in this way. So one example is Kafurian, and they propose a 2D CNN-based model that uses patches to increase the number of training samples and avoid overfitting during the training process. And the second group, they propose a 2-pass CNN based on a 2D patches with different MRI modalities in each, and finally concatenates each output for the final prediction. There are also some works that use a whole image, and they use 3D CNN utilizing shortcut connections between layers. And finally, at the Aslani et al. Group, they designed a deep 2D encoder-decoder CNN for the segmentation of MS lesions. This was also applied to 3D data, slice by slice, which are then concatenated to create 3D mask. It calls, I call it multi-branch CNN. We will use this work at the final page of my slide. Our method is based on 3 steps. One is the pre-processing step, in which we apply CLAHE. It's a contrast-limited adaptive histogram equalization method, which enhances the contrast and avoid distortion. This function is available on OpenCV or Python for enhancing contrast of images. We applied that to both of the modalities in our pipeline. From each modality, we extracted edge with Laplacian detector, and we'll add that as an extra channel to that modality. And then we normalize the intensities of the whole tensor with 0 mean and unit variance. So we will have a patch in a form of a box. First channel is original modality like flare, and the second channel is the extracted edges. So we extract patches from this image. The size of patches are 80 by 80 by 80 times 2. And the patches that we extract, they are mostly centered on lesion, around 60% of them are on the lesion, and the rest of them are non-lesion. And then we pass these patches to our neural network architecture for segmentation. The network runs on 2 different passes, that one of them uses flare modality and the other one uses T1. And then at the end, the result is concatenated for classification. For network architecture, our network architecture involves a novel spatial channel attention module that we add into different layers in the basic ResNet architecture. The spatial piece is a simple spatial attention And I explained in my previous paper presentation, unit R++, if you remember. The special piece is a simple special attention. For special attention, the query key and value are generated by a simple linear layer from the input to this module, which you can imagine it is a shape of D times H times W times C. As you know, in a deeper layer of ResNet, the value of C increases. So we start from 2 in the input, and then as we apply convolutions in the ResNet structure, we increases the C to 32 or 64 and so on, something like that. So the X is a tensor of shape of D times H times W times C. We create query key value by a linear layer from X, and then reshape that to N times C. N being the product of D, H, and W. Then we compute the tension using usual equation for attentions. Then applying softmax to that, and then multiplying by V. We get a result that is again a shape of N times C, which we reshape back to our input shape, and at the end we're gonna add it to the input feature X. This will produces the output from the special attention module. We call it S of X. We also create a channel attention module. Channel attention starts with the simple global pooling from the input feature X by doing a global pooling from a tensor of D times H times W times C. We will go to a tensor of shape of 1 by 1 by 1 plus times C. After that, we will have 2 fully connected layer, ReLU and sigmoid, to produce a single vector of a shape 1 by 1 by 1 by C. These are the scalars that we use to multiply to our input to produce the output from the channel module. So these channel attentions are created by these equations. The output from the whole spatial channel module is the sum of C of X plus S of X. As I said, this module is added 6 times in the different locations in ResNet architecture. Here we have the network training. We train our network with the combination of focal and Tversky loss function to handle imbalanced data. Tversky loss allows for assignment of different weights to false negative and false positive to improve the recall rate. But the problem with the pure Tversky loss is that it has a low convergence speed due to the segmentation of a small region of interest. And focal loss helps us overcome this issue, and it adds a parameter of gamma to control the segmentation of a small ROI. And the combination of focal loss and Tversky loss is defined by the following equation. You can see that PIC denotes the probability that pixel I is of lesion class C, and the same can be said for GIC, which is for ground truth. And PIC bar and GIC bar are defined for non-lesion class. So that the loss function, and as you see, we use the following values for alpha, beta, and gamma in this equation. We train the network using Adam optimizer with exponential decay and train it for 100 epochs with learning rate of 0.0001. To evaluate the output from the models, we use Dice coefficients and lesion true positive rate and lesion false positive rate and absolute volume differences. And about the data set, our data set is from ISBI challenge, which it's a very small data set, and the training set has just 5 subjects. We use 4 of them for training and 1 of them for validation. And image size is as following. You can see I mentioned, and the ground truth in this data set is is given by two different raters, which they don't necessarily agree with each other. And here is the result. Our result, as I said, we have 2 raters, and I told you that they are not necessarily agree with each other. As you see, we compare our method with one of our related works that I previously mentioned, the multi-branch CNN, which was trained only by the ground truths provided by R1. And as you see, our model improves in most of the metrics. That's it.